We take this module without A-level background and everything, right? So maybe you want to actually revise some of the topics from A-level. Okay, so luckily for you, actually in addition to teaching this module, I also teach PC1221, which is actually the bridging module for people without A-level. Okay, so you can actually also find some of my resources for PC1221 for here under the tutorial methods. Okay, so for PC1221, I actually happen to be the tutor, not the lecturer. Okay, so every Friday before tutorial, before PC1221 tutorial, I will upload some resources here. Okay, so for example, you can actually find the first tutorial for PC1221 here. Okay, so you just click that link. Okay, and then yeah, so you can see the first tutorial for PC1221. Okay, for PC1431, okay, we are going to upload the tutorial pages either tomorrow or Saturday. Okay, so any question about tutorial for 1431 start in week 4, so not next week. Okay, so any question about last lecture, last lecture? Okay, so if not, then now I'm going to start with the lecture. Okay, so this will be a continuation of our Tuesday lecture. Okay, so about kinematics in 2 dimensions and 3 dimensions. Okay. Alright, so for today's lecture, so I'm going to basically talk about another example, another common example of motion in 2 dimensions, which is basically something called circular motion. Okay, so circular motion basically refers to the motion of an object in a circle. Okay, so what you need to remember about circular motion, right, is that basically there are 2 kinds of acceleration. Okay, so whenever dealing with circular motion, right, remember 2 kinds of acceleration, not just one. Okay, and then these 2 acceleration actually have different purpose. Okay, so before I present some of the derivation, right, so as usual, right, it's better if I actually say some of the main point first. Okay, so the 2 types of acceleration and then later the derivation. Okay, so the first acceleration is something called centripetal acceleration. Okay, yeah, so centripetal acceleration, the purpose is actually to change the direction of the velocity. Okay, but this acceleration cannot change the magnitude. Okay, so here's the thing, right? So circular motion is an example of an object that moves in 2 dimensions. Okay, so that means, right, in order for the velocity to change, right? Okay, remember acceleration basically represents the change in velocity. Okay, in 1 dimension, right, the only way for the velocity to change, right, is that the magnitude will change, right? So velocity will change, for example, from 3 meters per second to 4 meters per second, right? So if that is the case, right, then the only way the acceleration can do, right, is basically to change the value of this velocity from 3 meters per second to 4 meters per second. Okay, but in 2 dimensions, right, change in velocity can arise because of 2 things, right? So either because the magnitude of the velocity change. Okay, so similar like in the 1 dimension case. But change in velocity can also happen when the direction of the velocity change, right? So that means if, let's say, initially you move this way, okay, and then you go that way, right? So basically I change direction. Okay, so in order to change direction, right, you also need acceleration actually. Okay? So that's basically the reason why for circular motion, right, you need 2 acceleration, because basically 1 acceleration is for changing the direction of velocity, and the other acceleration is to change the magnitude. Okay? Yeah, so as I said earlier, right, centripetal acceleration is the one that is responsible to change the direction of velocity, right? In order to make the object to move in a circle in the first place, right, in order to make the velocity, the direction of the velocity to keep changing to form a circle, we need centripetal acceleration. Okay? And in addition, right, if let's say the speed of the object also changes, so that means if when the object moves in a circle, the object moves faster or slower, then we also need another kind of acceleration called the tangential acceleration. Okay, so tangential acceleration is the one that is responsible to change only the magnitude, of the velocity, but no, not the direction. Okay, so tangential acceleration cannot change the direction. Okay, and then the direction of these two acceleration can also be seen in that screen, right? So centripetal acceleration will always be pointing toward the center of the circle. Okay, so that is always the case. Okay, and then for tangential acceleration, there are actually two possible directions. Okay, tangential acceleration can always be can be parallel to the direction of motion, right? So that means if the object moves clockwise, then the tangential acceleration can be either clockwise or anti-clockwise. So the point is that the tangential acceleration is always parallel to the direction of the velocity vector. Okay, but for the centripetal acceleration, it's always perpendicular toward the end of the circle, the center of the circle. Okay. Yeah, and then if you are asked to find the total acceleration, right, then you need to take into account not just the centripetal acceleration alone, not just the tangential acceleration alone, but the combination of these two. Okay, so by factor addition, right? So if you have basically you have two factors, right? Centripetal acceleration factor and tangential acceleration factor. So if you want to find the resultant factor, then you need to do factor addition, right? You need to do. Okay, so you need to do this thing. Okay, but if you still remember the concept of factor that I mentioned on Tuesday, right? Please note that this is not just the magnitude of centripetal acceleration plus the magnitude of tangential acceleration. Okay, because you see, in that equation, right, you have the arrow on top, right? So that means that is actually a factor expression. Okay, so you expect something like ijk inside. Okay, so for example, maybe centripetal acceleration is 3I, and then tangential acceleration is 4j. So the total acceleration is 3I plus 4j. Okay, so that is how to write total acceleration in factor form. Okay, but if you are only interested in the magnitude of the total acceleration, okay, then you can actually use Pythagoras. Okay, because if you see from that picture, right, centripetal and tangential acceleration, they are always perpendicular. Okay, so to find the magnitude of the resultant factors between two perpendicular factors, right, you can always use Pythagoras, right? So square root of centripetal square plus tangential acceleration square. Okay? Yeah, so any question up to here? Okay, so far it's okay, right? Okay, by the way, right, sometimes total acceleration, for total acceleration, right, we will not call this just total acceleration, right? Sometimes in the patient, we just refer to this as acceleration, right? So if let's say you have a patient, right, that deals with circular motion, right, and then the patient gives you acceleration, not centripetal acceleration, not tangential acceleration. The patient just say the acceleration is something. Okay, so that acceleration must refer to the total acceleration, right? So that means you need to be careful to resolve into tangential acceleration and the centripetal acceleration. Okay, yeah, so that's the concept part. Okay, so now the derivation part. Okay, yeah, so again, if you don't understand something here, right, then you can always ask me question. Okay, so derivation is actually important, right? Because it's possible, right, in the exam that we will ask you how to derive things. Okay, so it's better if you actually can understand each of the derivation that I will mention in lecture. Okay. So basically, for centripetal acceleration, we have a formula to calculate. Okay, and this slide basically shows you how to derive that formula. So in order to derive the formula for the centripetal acceleration, we are going to consider the situation called the uniform circular motion. Okay, so circular motion actually can be divided into two categories, right? Uniform circular motion or non-uniform circular motion. Okay, so uniform circular motion basically refers to the situation when the speed is constant. Okay, so when the patient says uniform circular motion, right, so that means, right, the object will move in a circle with a constant speed. Okay, so the speed will never change, will not slow down, will not speed up. Okay, but if you remember from earlier slide, right, you will still need acceleration, right, because in order for the object to move in a circle, right, the direction of the velocity will still need to change, and therefore you will still need to supply with acceleration. Okay, but of course, when the circular motion is uniform, then the only acceleration comes from centripetal acceleration, right? There is no tangential acceleration, okay, because there is no change in speed. Okay, so yeah, so basically the important point is that uniform circular motion means this one. Okay? And if there is no tangential acceleration, right, then to find the period of revolution. So period of revolution is basically just the time taken for the object to move one full circle. Okay, so this one, right, you can actually just use the formula, the well-known formula, right, distance over speed, right, because that formula, right, the t equals to s over v. Okay, so that formula will work if you don't have any acceleration, and acceleration is 0. Okay, and here, right, tangential acceleration is 0, so that's why to find the period, right, you can actually just use the formula, distance over time, and then the distance, right, so period is basically, again, the time to take one full circle, right, so the distance refers to the distance to travel one full circle. Okay, so that distance is basically the circumference of the circle, right, which is 2 pi r, right, so that's why you see the numerator is 2 pi r. Okay, and then the denominator speed is just v, right? The speed of the object that moves in the circle. Okay? Yeah, so especially note that this formula is only true for uniform circular motion. Okay, so I want to emphasize this, right? Because this possible, right, is quite often actually that in the test of exam, right, the students are asked to calculate the period of revolution for circular motion that is not uniform. And then they still try to use that formula. Okay, so normally, right, for term test, right, so because it's MCQ, right, so if you try to use this formula, right, so you will see that the answer is in one of the options, right, but of course that is not correct, right? That is just to trap you. Okay, so that's why you need to be careful, right, because otherwise then you will make mistake. Okay. Yeah, so remember that that formula is only for uniform circular motion. Okay. Now, assuming that there is no tangential acceleration, then we can actually derive the formula for centripetal acceleration quite easily by just using the picture. Okay, so hopefully you understand the meaning of that picture. Do you understand the derivation? Just by looking at the picture, can you actually derive it? Okay, so here's how to interpret that picture basically. Okay, so first of all, right, remember the assumption that the speed is constant. Okay, so that means, right, v at a certain time, right? So let's say you have an object that is initially over here. Okay, and then it moves to another location over here, right? The magnitude of these two v are the same, right? Only that the direction will change. Okay, so initially, right, the direction is this one, right, shown by the green arrow. Okay, and then later on, right, the direction will change to this one. Okay, so the one that is shown by the red arrow. The direction will change, but the magnitude is the same. Okay, so what we can do from this picture, right, is that we can actually compare the final velocity and the initial velocity, right? So the idea is this, right? So if let's say you imagine that this arrow you bring to here, right? In order to find out the angle between the initial velocity and the final velocity, right? You can denote the angle to be theta. Okay? And then, okay, so if you remember acceleration, right, it's basically defined as change in velocity over change in time. Okay, and then we can actually find this change in velocity by using t code. Okay? Yeah, so because you see that that triangle, right, the green and then the red and the black triangle actually will form some kind of like a right triangle. Okay, so you can actually use a t code to find delta v, the change in velocity, in terms of either the initial velocity or the final velocity. Okay, for example, can you see that delta phi, right, is equal to phi times tangent theta? Okay, so because tangent theta is opposite over adjacent. Okay, so if you take adjacent, right, so phi multiplied by tangent theta, right, you get exactly delta phi basically. Right? So up to here, any question? Okay, so I think you understand. Okay, because I see that you are not confused, right? I mean, it's like not like last week. I can see a lot of people confused, but it seems now like you seem to understand. So I trust that you understand. So if not, right, you can understand. Yeah. So delta phi equals to phi tangent theta. Okay, so again I ask again. So up to here is okay. Right. Okay. Then I continue. Okay. Now what we need to do, right, is to find the expression for tangent theta. Okay. To do that, right, we actually can use similar triangle, right, to notice, right, that this angle is actually the same as this angle. Okay, so that one is just math, right? You can actually just use some a little bit of geometry to see that the two angles that I circles are basically the same. which means, right, that you can actually also evaluate tangent theta from this triangle. Okay, from this triangle. Okay, but what is tangent theta if we look at that triangle? So the opposite will be delta r, right? So delta r represents basically the distance traveled by the object, right? Divided by the adjacent of that angle, which is the radius, right? So that's why here, right, you see tangent theta is replaced by delta r over r. Okay, so up to here, any question? Okay, so if not, right, you just rearrange this expression, right? Then you get this one. Okay, you basically remove v over r, and then you have delta r over delta t. Okay, but then if you notice, right, delta r over delta t, right, change in position over change in time, that is actually velocity, right? So we replace delta r over delta t by v. So you get to have v squared over r, right? So that's it. Okay, so yeah, that's it. That's the derivation for the centripetal acceleration. Okay. So any questions about this? Okay, so if not, right, so now we are going to talk about a more general case, which is a non-uniform circular motion. Okay, so remember the assumption previously, right, for uniform circular motion, right, we have been assuming that there is no tangential acceleration, right, the speed is constant. Okay, but non-uniform circular motion means that now we allow the speed to change also, right? So that means the object can speed up or can slow down. So in this equation, right, then both the tangential acceleration and centripetal acceleration may not be zero. Okay? But it turns out that the centripetal acceleration formula that we derived earlier will still work. Okay, so this formula, you can still take it as the formula for centripetal acceleration, right? So even though the derivation earlier, right, we only showed the derivation for the uniform circular motion case, but that formula turns out to also work for non-uniform circular motion, right? Okay, so basically you can just take v squared over r as just like a formula for centripetal acceleration. Okay. But for tangential acceleration, right, there is no such formula. Okay, so tangential acceleration, I mean, if you want to write out a formula, right, so that is basically this one. Okay, so tangential acceleration is simply defined as the derivative of speed. Okay, so not velocity, speed with respect to time. Okay, because if you differentiate velocity with respect to time, you will get basically the total acceleration. Okay, but if you only differentiate speed, okay, so that means not the factor form, just the speed, the magnitude of velocity with respect to time, then you only get the tangential acceleration. Okay? Yeah, but normally in the equation, right, the tangential acceleration is usually given. Okay, so normally problems involving non-uniform circular motion is that you are given the tangential acceleration, okay, and then maybe the initial velocity also, and then maybe you want to find the centripetal acceleration at a certain point, or maybe the final velocity or something. Okay, yeah. So this is actually another thing that I forgot to mention. So centripetal acceleration is still given by this formula, right? But now this centripetal acceleration will not be constant, okay? Because you see the formula is v squared over r, okay? But v keeps changing, right? Because non-uniform circular motion means that v can change, right? So that means, right, you cannot expect that the centripetal acceleration at, for example, time 0 seconds is the same as the centripetal acceleration at time 3 seconds, right? So it is possible the question might ask you, for example, calculate the centripetal acceleration at t equals to 5 seconds, and then the question gives you centripetal acceleration at t equals to 1 second, for example. Okay, so in that case, you cannot assume the centripetal acceleration to be the same. Okay? All right. So yeah, up to here, any question? Okay, so if not, right, then the next thing that I want to talk about, right, will be a special case of non-uniform circular motion when the tangential acceleration is constant. Okay, so if you remember from last week's lecture, right, I mentioned that when dealing with constant acceleration, right, you can actually use very useful three equations called three kinematic equations. Okay, so for circular motion, right, it turns out, right, you can also use these three kinematic equations if the tangential acceleration is constant. Okay, so you don't need to make sure that the total acceleration is constant, right? For kinematic equation to work in circular motion, right, it is sufficient that only the tangential acceleration is constant. Okay. But then, right, if you notice, right, with these three kinematic equations, so even though these are very similar to the kinematic equation that I mentioned last week, but you might notice some difference, especially in the things that I highlighted in red. Okay, so what, can you see the difference, by the way, between these three kinematic equation and the one last week? So what are the differences? Can you see on the, what is the thing that I highlighted in red? S. And then A tangential. Okay, if last week you still remember, so what are the kinematic equations? Instead of S, we have delta something, right? And then instead of tangential acceleration, we have A, right? The total acceleration. Okay, yeah, so the two main difference between kinematic equations in linear motion and circular motion, right, is that, first of all, right, any delta x, any displacement that you see in the kinematic equation, right, you replace by distance. Okay? Yeah, for example, right, if let's say, normally in linear motion, right, if the object moves from this location to this location, and then that location, right, then in the kinematic equation, right, you just take the change between final and initial, right, the displacement basically. Okay, but for circular motion, right, the S actually refers to the distance. Okay, so that means, for example, if the object moves one full circle, right, then your S is not 0, right? Because even though it returns to the original location, okay, but because you take distance, right, so you need to take into account the total distance traveled, which is 2 pi r. Okay? And then another thing, right, is that the A that appears in the kinematic equation for circular motion refers to only the tangential acceleration, so not the total acceleration. Okay, so even though maybe the equation gives you the total acceleration, right, but if you want to apply kinematic equation for circular motion, okay, so you need to find the tangential acceleration first, and then it is the tangential acceleration that you sub into the equations. Okay? Yeah, so after here, an equation. Okay, so if not, right, then basically that's it. That's the theory that I want you to understand. Okay, so now we are going to see an example, and then we will do the assessment. Okay, yeah, so this is basically the example, right? So this example basically shows you two types of equations involving non-uniform circular motion. Okay. Okay, so basically this is the question. Let me just draw. Okay, so there is this car that moves in a circle with radius of 120 meters. Okay, so the initial speed is given, which is 40 meters per second. Okay, and then the question is this, right? So the car will move in a circle, right? And then eventually, right, it will move one lap, right, one full circle. Okay, and then you want to find the period, basically, what is the time taken to reach one full circle. Okay, and then to do so, right, you need to assume two possible scenarios. Okay, so the first scenario, right, is that the speed is constant. Okay, and then for the second scenario, the speed decreases uniformly. Okay, for the situation where the speed is constant, right, it should be easy, right, because this is the example of uniform circular motion. Okay, so if you still remember from what I just explained, right, for uniform circular motion, how do you find the period? T is, what's the formula for T? Yeah, 2 pi r, right, the circumference and the total distance divided by speed, right? And then everything is given, right? You have the radius, you have the speed, then that's it, right? You can calculate. What's the answer? think 18.8. I think, okay, so if I calculate right. Okay, so that's correct? Okay, good. Okay, so now for the second part. Okay, so for the second part, so how do we do this? So the speed increase uniformly. Okay, so here's the thing, right? So even though the question says something like uniform, right? But it does not mean that the motion is a uniform circular motion, right? Because, okay, remember the meaning of uniform circular motion is that the speed is constant, right? But here, right, the speed decrease, only that the change in speed, right, is uniform, is constant. So in that case, right, if you remember, right, what is the change in speed over time? The rate of speed over time is, yeah, what is that? Acceleration, is it acceleration? Speed, right, change in speed, not change in velocity over time. Change in speed over time is the tangential acceleration, right? Yeah, so tangential acceleration is constant. Okay, but if you remember what I just explained like a few seconds ago, so what does that mean? Constant tangential acceleration means that we can use kinematic equation, right? Yeah, we can use kinematic equation. So yeah, that's what we are going to do now. But which kinematic equation should we use? So we want to find time. We have the initial speed. We have radius. If we have the radius, right, that means, right, we will have the distance, right? Distance is basically just the circumference, 2 pi r, right? Okay? But what we don't have is the final speed, right? The question does not give you the speed after the car goes back. Okay? So that means which kinematic equation do we use? Oh, sorry, yes, okay, so I didn't read the equation properly. So final speed is actually given. Okay? Okay, good. So that means, right, final speed is half v0. Yeah, so which kinematic equation should we use? Okay, so, yeah, which one? Okay, this one, right, Vf. Okay, because our objective is to find time, right? So we can first use this one, Vf equals to v0 plus v. Okay, but remember the particular motion, right, the A refers only to tangential acceleration. Okay? And then we start in Vf equals to half v0. Okay, so we get this one. Okay, but what is the tangential acceleration here? How to find the tangential acceleration? It's not given, right? So how do we continue from here? Yeah, so actually in this case, we actually need to use 2 kinematic equations, not just one. Okay, so remember we have 3 kinematic equations, right? So that means if you use one kinematic equation, right, and then you still cannot solve, right, then you just try to use another kinematic equation. Okay, so we write this as equation 1. Okay, and then now we try to use another kinematic equation. So which one should we use? We can use, for example, this one, Vf squared equals to v0 squared plus 2as. Okay. So again, Vf final speed is half v0. Okay, and then the distance. Okay, even though the object goes back to the original point, right? And remember, for circular motion, you use distance, right, not displacement. So that means you suck in 2 pi r, right? Not 0. Okay, then this will be your equation 2. Okay, so you have 2 equations and 2 unknowns, right? You don't know tangential acceleration, you don't know time. Okay, but you also have 2 equations, right? Equation 1 and equation 2, right? So you can simultaneously solve these 2 equations to find time, right? So from these 2, you can find what is time. Okay? Yeah, what's the answer? Maybe some of you have gotten the answer. 25. Okay, if I make the calculation correctly, then it's okay. So any question about this example? Oh yeah, that's actually true, yes. Okay, so that's actually a good point mentioned by one of your friends. So if you remember right, actually we have the 4 kinematic equation. So this is actually not listed in the 3 kinematic equation that I mentioned earlier. But actually last week lecture, I mentioned that there is the 4 kinematic equation, which is basically this one. Delta x equals to Pi plus Pn over 2 times T. So we can also use this fraction of the kinematic equation for circular motion. Like what you need to do, right? You just change this delta x, which we have like the distance. And then from here, right, you can actually find time only by using one equation. Okay, so that's this one. Okay, so I didn't know. Okay, good. Okay, yeah. So that method. Yeah. Any other point that you want to or question? Okay, so it's now right, so it's time for the assessment. So I have opened the assessment. Okay, so you try for 5 minutes, then I will quickly go through.
这也不是每天晚来，真的是1个月。这里吃呀？还去别的地方对吧？你还坐车地铁？我觉得你家是买车的，对，不然这几天买车在这边。好贵耶！帮你按一下。怎么了？啊？理解小哥，又是2题啊！
not under the money. So what you said before for checking the 會咁啊？打聲嘅。
错的啦。空了怎么办？会按一下，按也没用吧？这个不是一样，可是你翻开你发现，看它最后结果太痛了。我今天还发现高的都是吗？这个来做吧。Acceleration 不是黄色吗？他讲黄色吗？没有黄色。Increasing uniformly 了。Speed increases uniformly 不是黄色，是 acceleration increasing。Speed increases uniformly 啊，就是 acceleration 等于0啊。黄色的是啊。后面讲 acceleration 等于5啊。黄色的是吧？就他说你走 acceleration F， 那你走你的 initial acceleration， 你可以用这个法，这是有 B F 有 A 有 Q。你说呢？笑死！这不是拿到15呗？不是 VI， 你找的不是 VI， 找的是 initial。哦，initial 啊，我也是。我刚跟你算一样，我跟你找 VI。他不是，就是他的身份不是有地方。对啊，为什么啊？一方面跟你科技不一样，对，对，看哪里好？
Okay, so have you got the answer? What is the answer? Okay, so let's do this equation together. Okay, so basically this is very similar to what I just explained in the example just now. You have a non-uniform circular motion, but with constant tangential acceleration because the speed increase uniformly. Okay, so first of all, to do this equation, you need to write down all of them under this given first. Okay, so basically we are given the radius, which is 100 meters. Okay, and then initial time, okay, let's call this Ti, which is it's the final time. Okay, so let's call this T, so T is 1 second. And when T equals to 1 second, okay, so the acceleration is 5 meters per second squared. Okay, what acceleration is this? Okay, remember if the equation only says acceleration without saying tangential or centripetal, right? We assume that this is total acceleration. Okay, so it's not tangential acceleration; it's total acceleration. Okay. Yeah. So later on, if you want to use kinematic equation, you need to find the the tangential acceleration. Okay, and the speed is also given, right? So the speed. Okay, so let's call this speed f. Right? So speed is 20 meters per second. Okay, and then you want to find the acceleration at times t equals to 0. Okay? Yeah, so how to do this? Okay, so first of all, right, because the patient asks you to find total acceleration, right, then you just use the formula first for total acceleration. Okay, so how to find total acceleration for circular motion? You take square root of tangential acceleration square plus centripetal acceleration square. Okay, so tangential acceleration is not given. Okay, so later we are going to find. Okay, but centripetal acceleration we have a formula, right? So what is the formula? If you remember. V square over r, right? And then we square it. Okay, but what phi is this? Is this phi the 20 meters per second? No, right? It's not 20 meters per second, okay? Because the question asks you to find total acceleration at t equals to 0 seconds. Okay, but 20 meters per second is the speed at t equals to 1 second. Okay, so that means you need to write down your phi as phi, right? Phi is the speed at t equals to 0 seconds, which is also not given. So you have two unknowns here, the tangential acceleration and also the initial speed. Okay, but to find the tangential acceleration, right, we can actually use these two information. Okay, because we have the total acceleration and the final speed. So we can also use, okay, let's call this okay, A total prime is basically for the initial total acceleration that we want to find. Okay, and then A total without prime is basically to refer to the one that is given, which is 5 meters per second squared. So 5 equals to square root tangential acceleration squared plus the centripetal acceleration squared at final time, right, which is phi f squared over r squared. Okay? Then from here you can start in the number because phi f is given, so you can find the tangential acceleration. Okay? Yeah, then after you have found the tangential acceleration, then you can simply use kinematic equation to find phi I, right? We can use phi f equals to phi I plus tangential acceleration times t. Then from here you can find phi I. Okay, then you sub in everything back to this expression. Okay, and that's it. Alright. Yeah, so the detail I think you can work out yourself. Okay, so yeah, any question about this whole thing? Okay, so if not, then I think I will end this lecture now. Okay, so we end quite early, actually 1 minute earlier. Okay, but of course, if you have patience, you can ask me. And if you still haven't gotten this module, you cannot access your quiz, you can also write your attendance here. Okay, then I'll see you all next week.
你要送 VA 对啊。
看到没有？没错吧？这样？对啊，0.5，0.5是 VI。啊？哦，对吧？那我的是搞错了吗？我搞错了。3不是啊，是3，手也白了。哇操，这搞错真的是。啊？ 黑 VS 变成
那我用它明天
你变到哪里啊？
没有 VS 嘛，对不对？然后 A 就是有，
因为你的参与不懂的，
就是等1秒，等1秒。因为我们用的很久的时候就是
那我用这个不可以吗？用这个不可以吗？
你用 S，
有 S 吧？太暗了。
太讲太讲，
他又没有讲这一
他没人圈，
我没人圈啊。
对呀、
小点对。
三一啊，3看什么？
没意思。
哦
4.16。
4.1，
4.2，这是4.2，它是4.2。
因为这个有个时代他忘了写。
这4.2。哇，还有这一题啊！行啊行啊。